Does reality truly exist if no one is observing it? How can two particles on opposite sides of the universe instantly influence each other? Is it possible that every decision we make creates a parallel universe? If time can reverse at the quantum level, what does that mean for our future? Could the human brain operate like a quantum computer? Are we living in a reality where everything is invisibly interconnected? Welcome to the perplexing world of quantum mechanics, where the rules we think govern reality break down, and the universe reveals itself as something far stranger than our everyday experience suggests. The mysterious truths of quantum mechanics. Imagine tossing a pebble into a pond. The ripples spread out, graceful and predictable. Now, what if the pebble could behave both like a ripple and as a solid object at the same time? Quantum mechanics is a branch of physics that studies the smallest building blocks of the universe, particles like electrons, photons, and quarks. Yet the more we look, the less solid reality seems to become. This section will explore three of its most mysterious phenomena: wave-particle duality, superposition, and quantum entanglement. Wave-particle duality is the idea that light and matter can behave both as particles and waves, depending on how they're observed. Imagine asking someone whether a coin is heads or tails, and their answer changes depending on how closely you're looking. The double-slit experiment. In this iconic experiment, scientists shot particles, like electrons or photons, at a barrier with two slits. Behind the barrier was a screen to capture where the particles landed. Step 1. When the particles were observed closely, they behaved like tiny marbles, forming two distinct lines on the screen, one behind each slit. Step 2. When not observed, the particles acted like waves, spreading out and forming an interference pattern of many lines, as though the particles had passed through both slits simultaneously and interfered with themselves. Simplified explanation: think of a particle as a traveler facing a fork in the road. When no one is watching, the traveler takes both paths at once, exploring every possibility. But the moment you watch, the traveler chooses one path, as if responding to your gaze. Why it's strange? This suggests that the mere act of observing can change the fundamental behavior of matter. Is reality shaped by observation? And if so, what does that mean about the universe when no one's watching? Quantum superposition. In classical physics, an object is either here or there, in one state or another. Quantum mechanics introduces superposition, where particles exist in multiple states simultaneously until measured. Schrödinger's cat thought experiment. A physicist, Erwin Schrödinger, imagined placing a cat in a box with a vial of poison, which would break if triggered by a random quantum event. Until someone opens the box, the cat exists in a superposition of states both alive and dead. Imagine flipping a coin and sealing it inside an envelope. To you, the coin is both heads and tails at the same time, because you haven't seen it yet. It's only when you open the envelope that the coin chooses a side. Why it's strange? Superposition challenges the idea of objective reality. If particles exist in multiple states until observed, is the universe inherently uncertain? And how does reality decide which state to take when observed? Quantum entanglement. Entanglement occurs when two particles become so deeply connected that the state of one instantly determines the state of the other, no matter how far apart they are, even if they're on opposite sides of the universe. Einstein's skepticism. Albert Einstein famously called entanglement spooky action at a distance, because it seemed to defy the speed of light, the universal speed limit. Yet experiments have repeatedly confirmed this phenomenon. Simplified metaphor: imagine you have a pair of gloves. You send one glove to the moon and keep the other on Earth. Without looking, you don't know which is the left glove and which is the right. The moment you check the glove on Earth and see it's the left one, you instantly know the glove on the moon is the right, even though no information traveled between them. Entanglement suggests that particles can remain connected in a way that transcends space and time. Could this imply a deeper, hidden layer of reality where everything is interconnected? Questions to ponder. If observing particles changes their behavior, does that make us co-creators of reality? How can particles influence each other instantaneously across vast distances? Is the universe fundamentally random? Or is there an underlying order beneath the quantum chaos? Quantum mechanics challenges our deepest assumptions about reality. Wave-particle duality blurs the lines between objects and actions. Superposition raises questions about the nature of existence, and entanglement hints at a universe where everything is interconnected in ways we're only beginning to grasp. This is just the beginning of our journey into quantum science. As we dive deeper, these mysteries will intertwine with questions of philosophy, consciousness, and the very fabric of time. But for now, quantum mechanics reminds us of a humbling truth. The universe is far stranger and far more wonderful than we ever imagined. Philosophy and quantum mechanics. Quantum mechanics doesn't just alter our understanding of physics, it challenges our fundamental beliefs about reality, existence, and the nature of the universe. It brings us face to face with questions that philosophers have grappled with for centuries. Could quantum mechanics provide the missing link between science and philosophy? In this section, we explore the fascinating relationship between quantum theory and philosophical inquiry. The observer effect. Does reality exist without observation? The observer effect in quantum mechanics suggests that the mere act of observing a quantum system can change its behavior. In the famous double-slit experiment mentioned earlier, particles like electrons or photons behave as waves when unobserved, and as particles when observed. But here's the philosophical twist. If observation affects reality, then can we really say that the world exists independently of us? Does the universe only decide its state when we look at it? This is a powerful philosophical question that echoes the debate about whether existence requires a mind to perceive it. Simplified explanation. Imagine you're trying to catch a butterfly in the wild. Every time you approach it, the butterfly flutters away, changing its position and behavior. If you stand still and don't try to catch it, the butterfly behaves in its natural way. The act of trying to catch it or observe it changes what it does. This is like what happens at the quantum level. Our attempt to measure something changes its state. Philosophical connection. This idea mirrors solipsism, a philosophical theory that suggests only the mind of the observer can be known to exist. In quantum mechanics, it's almost as if reality isn't truly there until we observe it. Could our minds actually be shaping the world around us? If so, what does that say about free will and our place in the universe? Questions to ponder. If the act of observing creates reality, what does that say about the world when we're not looking? Can we ever truly know the universe if our perception of it always shapes it? The multiverse hypothesis, a universe for every possibility. Quantum mechanics also suggests that, when faced with multiple possible outcomes, particles don't just pick one, they exist in all possibilities simultaneously until measured. This leads to the many worlds interpretation, which proposes that every time a quantum event occurs with multiple possibilities, the universe splits into separate branches, each representing one of the possible outcomes. Essentially, every decision, every quantum event creates a new universe. Simplified explanation. Imagine you have a coin and you're about to flip it. In the quantum world, the coin doesn't just land on heads or tails, it lands on both, in separate worlds. In one universe, it's heads, in another, it's tails. Every possible outcome of every quantum event exists in its own parallel universe. This theory raises the idea of determinism versus free will. If every possible outcome exists in a parallel universe, does that mean we're simply along for the ride, with no true choice? Or does the fact that we experience one outcome imply that we are actively shaping our reality? Questions to ponder. If there are infinite universes, does it mean all possibilities are actualized, or is there still a guiding hand behind it all? What does this say about the role of free will in our lives? Are we simply living out one branch of the many possibilities? Determinism versus free will. Does the quantum world allow for both? In classical physics, the universe was thought to be deterministic. Everything happens because of prior causes, like the turning of a clock. But quantum mechanics doesn't fit this model. Quantum mechanics tells us that at the microscopic level, events are not entirely predictable and chance plays a significant role. This creates an interesting paradox when thinking about human behavior. Is everything determined by the laws of physics, or do we have the power to make choices that aren't preordained? Think of a rolling dice. Classical physics would say the dice's outcome is determined by its starting position, how fast it rolls, and all the forces acting on it. But in quantum mechanics, the dice could land on several faces at once, and it's only when we look at it that we see which face it lands on. Could our decisions be more like this quantum roll of the dice? This aligns with a long-standing philosophical debate. Is our universe deterministic, where everything happens for a reason, or is there room for randomness and free will? Quantum mechanics, with its inherent unpredictability, seems to suggest that randomness plays a role in shaping our world. But what does that mean for the human experience of choice? Questions to ponder. If quantum mechanics allows for randomness, does that free us from being controlled by the laws of physics, or does it create a different kind of order? How does this randomness relate to the concept of free will? If we're free to choose, is it random, or is there a deeper purpose behind our decisions? In this section, we've explored how quantum mechanics doesn't just change our view of the universe, it compels us to revisit age-old philosophical questions. From the observer effect's challenge to objective reality, to the multiverse's implications for free will, quantum theory forces us to reconsider what we think we know about existence. Quantum mechanics isn't just a tool for physicists, it's a bridge between science and philosophy, urging us to ask deeper questions about the nature of reality, consciousness, and choice. As we continue to explore these ideas, we'll see how quantum mechanics intertwines not only with the smallest particles, but also with the deepest questions about our place in the cosmos. Quantum mechanics and consciousness. The intersection between quantum mechanics and consciousness is one of the most intriguing and speculative areas in modern science. Does quantum theory hold the key to understanding consciousness? Could our minds be operating on quantum principles, giving rise to thoughts, emotions, and self-awareness? This section explores how quantum mechanics might be connected to the very nature of consciousness, blurring the lines between physics, philosophy, and psychology. Quantum brain hypothesis. Could the brain work like a quantum computer? One fascinating theory is that the brain could operate like a quantum computer, using the principles of superposition and entanglement to process information in ways classical computers can. The idea is that quantum effects might be occurring within our neurons, influencing how we think, perceive, and experience the world. Imagine trying to solve a puzzle by checking all the possible answers one at a time. A classical computer would do this in a linear fashion, one possibility after another. But a quantum computer, using superposition, could check all possibilities at once much faster. If our brains worked this way, it could explain the speed and complexity of human cognition. Supporting evidence. Some scientists point to microtubules, tiny structures within our neurons, as potential quantum processors. These microtubules might be able to support quantum states, which could allow the brain to process vast amounts of information at incredible speed. The hypothesis was notably proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff in their theory of orchestrated objective reduction, which suggests that consciousness arises from quantum processes within the brain. Why it's fascinating? If the brain operates on quantum principles, it would mean that our minds could be far more complex than we currently understand. It might also explain the subjective quality of consciousness, why we experience thoughts and emotions rather than simply processing information like a computer. Questions to ponder. If quantum mechanics is involved in consciousness, could we ever fully understand how thoughts arise? Could quantum processes help explain the hard problem of consciousness? Why subjective experience arises from objective brain activity? Panpsychism and quantum physics, consciousness in every particle. Panpsychism is the philosophical theory that consciousness is a fundamental property of all matter. In other words, everything down to the tiniest particle has some degree of consciousness. Some proponents of this view argue that quantum mechanics could provide the framework for understanding how consciousness pervades the universe. Simplified explanation. Imagine you have a drop of water. In classical physics, you could describe it purely by its physical properties, its weight, its temperature, etc. But what if, on a deeper level, the molecules inside the water also had an awareness of their environment? Panpsychism suggests that consciousness isn't limited to humans or animals. Instead, it's a fundamental feature of the universe. Quantum connection. Quantum mechanics hints at the idea that consciousness could be an intrinsic feature of matter. For example, quantum coherence, the ability of particles to remain in a superposition of states, could be the physical manifestation of a deeper, universal consciousness. This idea aligns with David Bohm's theory of the implicate order, which suggests that everything in the universe is interconnected through a deeper layer of reality that could also involve consciousness. Why it's fascinating? If consciousness is embedded in the very fabric of matter, it suggests that the universe itself could be conscious. In this view, every atom, every photon, and every quark might have a tiny, rudimentary form of awareness. This could radically change how we think about the mind-body problem and our relationship with the universe. Questions to ponder. If every particle has consciousness, does that mean we are connected to everything around us in a profound way? Could quantum processes in particles explain the nature of subjective experience? Integrated Information Theory, IIT. Could the universe itself be conscious? One of the most ambitious theories of consciousness is integrated information theory, developed by neuroscientist Giulio Tononi. IIT proposes that consciousness arises from the degree to which a system can integrate information. The more interconnected and integrated the system, the more conscious it is. This theory suggests that consciousness might not be limited to humans or animals, but could be a property of any system that integrates information in a sufficiently complex way. Think of a light bulb. When it's on, it illuminates the room, but when you turn off the switch, the light goes out. In a way, the light bulb integrates the flow of electricity, but it's not conscious. Now, imagine a more complex system, like the brain, which integrates vast amounts of information across billions of neurons. According to IIT, the more information that's integrated, the higher the level of consciousness. Quantum connection. If IIT is correct, and consciousness is about integrating information, then quantum mechanics could play a key role. Quantum coherence, the ability of quantum systems to remain in a state of superposition and interact with one another, might allow for a higher level of information integration. In this way, the quantum world might help explain the emergence of consciousness in complex systems. IIT could provide a framework for understanding not only human consciousness, but also the consciousness of the universe itself. If the universe is a vast network of interconnected systems, each integrating information in complex ways, could it be that the universe itself has some form of awareness? Questions to ponder. If IIT is correct, could the universe be conscious in the same way that our brains are conscious? What would it mean if the universe as a whole had an awareness of its own existence? In this section, we've explored how quantum mechanics could be linked to consciousness, offering new possibilities for understanding the mind. From the idea of the brain operating as a quantum computer, to the radical suggestion that consciousness may be a fundamental property of matter, quantum theory opens up new avenues for thinking about awareness and existence. Quantum mechanics, with its strange and counterintuitive properties, challenges our understanding of reality, and in doing so, it may be pointing us toward a deeper, more interconnected view of consciousness. If consciousness arises from quantum processes, the universe might be far more conscious than we ever imagined, perhaps even in ways we are yet to comprehend. Quantum mechanics and time. Time is something we all experience, seconds ticking by, days passing, and memories fading as the years go on. But quantum mechanics suggests that time might not be as straightforward as we think. In fact, quantum theory challenges our most basic understanding of time, raising deep philosophical questions about its true nature. Could time be more fluid than we've ever imagined? Is it a fundamental part of the universe, or could it be an illusion? In this section, we'll explore how quantum mechanics reshapes our concept of time and what it means for our understanding of the universe. Non-linearity of time. Does time flow in one direction? In classical physics, time flows in one direction from the past to the future. This idea is deeply rooted in the second law of thermodynamics, which states that entropy, or disorder, tends to increase over time, creating a natural arrow of time that moves forward. However, quantum mechanics presents a different picture. At the quantum level, time may not flow in a strict, linear fashion. Imagine you're watching a movie. As the story progresses, things happen in sequence, first this, then that. But at the quantum level, the sequence of events might not always be fixed. It's as though you're watching a movie where the scenes could play in any order, and the story might change depending on your perspective or how you're observing it. Time itself could be much more flexible than we experience it in our daily lives. Why it's strange, in quantum mechanics, particles don't always behave as though they follow a strict timeline. For instance, certain quantum processes can seem to reverse time, where particles appear to go backward in time, which challenges the idea of a universally directed flow of time. Quantum mechanics example. Quantum particles can travel backward in time according to the Feynman diagrams in quantum field theory. These diagrams depict particles as traveling through both forward and backward directions in time, essentially reversing the arrow of time under certain conditions. Questions to ponder. If time can flow backward at the quantum level, what does that say about our perception of the past, present, and future? Could the experience of time we have in our everyday lives be an illusion, a consequence of our limited perspective? Time reversal symmetry. Could time run backward? One of the most mind-bending implications of quantum mechanics is the idea of time reversal symmetry. This principle suggests that the laws of physics are the same whether time flows forward or backward. If you could rewind a quantum process, the physics would work just as they did going forward. In other words, if you could reverse the motion of a quantum system, it wouldn't violate any physical laws. Think of a video of a ball bouncing. If you play it backward, the ball seems to jump up from the floor, defying gravity. But in the quantum world, the ball's behavior would not change if played backward. The particles and forces involved would still obey the same fundamental rules, whether time is moving forward or backward. Why it's strange, time reversal symmetry in quantum mechanics challenges our everyday experience. We never see time rewinding in the macroscopic world. We observe things breaking, aging, and decaying in one direction only, forward. Yet, at the quantum level, particles behave as though they could reverse direction, suggesting time itself may be a construct based on our perception. At the subatomic level, certain particles like photons and electrons behave symmetrically under time reversal. If you were to reverse the direction of time for a quantum event, the system would evolve in precisely the same way, leading scientists to wonder if time's flow is an artifact of our observations. Questions to ponder. If time is reversible at the quantum level, does that mean our concept of time itself is just a mental construct? Could this symmetry have real-world consequences, such as in the development of time travel technologies? Quantum time travel. Is time travel possible? Could quantum mechanics make time travel possible? While time travel has long been a staple of science fiction, quantum mechanics opens the door to a theoretical possibility. The strange behaviors of particles at the quantum level, like superposition and entanglement, suggest that time may be more flexible than we realize. Could we, in theory, travel backward or forward in time? Simplified explanation. Imagine you're standing at a fork in the road, and both paths lead to the same destination. In classical physics, you can only take one path, but in the quantum world, there's a chance both paths are traveled simultaneously, with each one existing in a different timeline. It's as if you're living in two parallel realities, one where you choose one path, and another where you take the other. While actual time travel is still the stuff of fiction, some theoretical physicists suggest that quantum mechanics could allow us to move through time in ways we can't fully comprehend yet. One of the key ideas here is wormholes, theoretical shortcuts in space-time that could allow travel between different points in time and space. Quantum mechanics example. A specific type of quantum phenomenon called closed time-like curve suggests that time loops where the future influences the past could exist within the framework of general relativity. These theoretical time loops have been studied in the context of quantum particles, and they might be the key to understanding time travel. Questions to ponder. If quantum mechanics allows for time loops, could we travel back to the past and change history? What would happen to the laws of causality if time travel were possible? Quantum mechanics fundamentally challenges our understanding of time. From non-linearity to time reversal symmetry and the possibility of time travel, quantum theory presents a view of time that's far from the fixed, unidirectional flow we experience in our daily lives. At the quantum level, time is not an absolute, steady force, it's a malleable, fluid aspect of the universe. As we continue to explore the relationship between quantum mechanics and time, we may find that our perception of reality itself is shaped by deeper, quantum-level processes. Perhaps in time, the mysteries of time travel, time reversal, and the true nature of temporal flow will be unraveled, giving us an entirely new perspective on our place in the universe. The future of quantum science. Quantum mechanics isn't just about understanding the fundamental nature of reality, it's driving the next technological revolution. While we've already explored some of the mind-bending concepts that quantum mechanics presents, its potential applications in the future could change everything from how we compute to how we communicate. This section explores the cutting-edge developments in quantum science and what they might mean for the future of humanity. Quantum computing, the next leap in technology. Quantum computing harnesses the strange properties of quantum mechanics, such as superposition and entanglement, to solve problems that classical computers simply cannot. Unlike classical computers, which process information as bits, either 0 or 1, quantum computers use quantum bits, or qubits, which can represent both 0 and 1 at the same time due to superposition. This gives quantum computers the ability to perform many calculations simultaneously, opening up possibilities for solving complex problems in seconds that would take classical computers millennia. Think of a classical computer like a person who can only check one box at a time on a list. A quantum computer, on the other hand, can check all the boxes at once, dramatically speeding up problem-solving processes. Quantum computers could revolutionize fields like cryptography, material science, drug discovery, and more. Problems that are currently intractable, such as simulating molecules for new drug compounds or optimizing complex systems, could soon be solved by quantum computers. Example: Google's Sycamore quantum processor achieved quantum supremacy in 2019 by solving a problem that would have taken the world's most powerful classical computer 10,000 years to solve within just 200 seconds. This marked a significant milestone in demonstrating the real-world potential of quantum computing. Questions to ponder. How soon will quantum computers be able to solve practical problems we cannot yet imagine? What ethical implications could arise as quantum computing accelerates developments in fields like artificial intelligence and cryptography? Quantum cryptography, the future of secure communication. Quantum cryptography uses the principles of quantum mechanics to create secure communication channels that are theoretically impossible to hack. The most famous application of quantum cryptography is quantum key distribution (QKD), which allows two parties to exchange encryption keys securely. If anyone tries to intercept the communication, the quantum system detects the intrusion and changes the key, rendering the hack useless. Simplified explanation: imagine sending a secret message inside a sealed envelope. In classical systems, if someone intercepts the envelope, they can open it and read the message. In quantum systems, if anyone tries to open the envelope, the quantum properties ensure that the contents are changed, making it obvious that someone was tampering with the message. Quantum cryptography could lead to virtually unbreakable security systems. Governments, banks, and organizations could use QKD to ensure that sensitive data remains protected from hackers and cyber threats, even in a future where supercomputers could break current encryption methods. Example: in 2017, China launched the world's first quantum satellite, which successfully demonstrated the use of QKD to establish secure communications between ground stations. This marked a significant step toward the global deployment of quantum communication systems. Questions to ponder. How will quantum cryptography change the way we think about privacy and security in the digital age? Could quantum communication lead to a new era of trust and transparency in global systems? Quantum sensors, revolutionizing measurement and detection. Quantum sensors leverage the unique properties of quantum systems to make incredibly precise measurements that classical sensors cannot achieve. These sensors can detect incredibly small changes in magnetic fields, gravitational waves, and even time. They hold the potential to revolutionize fields like navigation, geology, and medical diagnostics. Imagine you're trying to measure the tiniest vibrations on a surface. A classical sensor might miss the smallest signals, but a quantum sensor, like a super-sensitive microphone, can pick up every detail no matter how small. This precision opens up entirely new possibilities for measuring forces in the universe. Quantum sensors could allow for GPS-independent navigation, where extremely precise measurements of gravitational fields can track positions without relying on satellites. Additionally, quantum sensors could lead to breakthroughs in medical imaging, allowing for earlier detection of diseases or abnormalities on a molecular level. Example: quantum gravimeters are already being used to measure the Earth's gravity with extreme precision. This could help scientists detect underground resources, map geological structures, or even monitor natural disasters like earthquakes and volcanic eruptions in real time. Quantum energy, harnessing the power of the quantum world. One of the most ambitious goals of quantum science is to harness quantum effects to create more efficient energy systems. For example, quantum mechanics could play a role in developing quantum batteries or improving solar panels by using quantum properties to capture more light and convert it into energy. Simplified explanation: imagine a solar panel that works like a sponge, absorbing as much sunlight as possible. Using quantum mechanics, we could make the sponge much more efficient, allowing it to soak up more light and convert it into usable energy. Example, researchers are already experimenting with quantum dots, tiny semiconductor particles that can capture sunlight at higher efficiency than traditional solar cells. These breakthroughs could help make renewable energy more efficient and affordable, accelerating the shift to cleaner energy sources. Questions to ponder. Could quantum energy solutions help us tackle the global energy crisis? How soon could quantum energy technologies become commercially viable, and what impact will they have on the environment? Quantum science is not just a theoretical pursuit, it's the gateway to a new technological era. From quantum computing and cryptography to the development of ultra-sensitive quantum sensors and more efficient energy systems, quantum mechanics holds the potential to revolutionize how we live, work, and interact with the world. While these technologies are still in the early stages of development, they're already showing promise. As we continue to unlock the secrets of the quantum world, we may find ourselves on the cusp of breakthroughs that will shape the future in ways we can't yet fully imagine. Real-world applications of quantum mechanics. Quantum mechanics, with its strange and fascinating properties, is not just a theoretical framework, it's already making an impact in the real world. While much of quantum physics seems abstract and theoretical, its principles are increasingly being applied to solve practical problems. From revolutionizing medical technologies to transforming how we navigate and communicate, quantum mechanics is paving the way for groundbreaking innovations that could change the way we live. In this section, we'll explore some of the most promising real-world applications of quantum mechanics and how they're already shaping industries and research. Quantum medical imaging, a new frontier in diagnostics. Quantum mechanics is starting to make its mark in the medical field, particularly in medical imaging. Quantum technologies, such as quantum sensors, can provide unprecedented sensitivity in detecting tiny changes in biological systems. This could lead to more accurate and earlier detection of diseases like cancer, neurological disorders, and heart disease, potentially saving lives by spotting issues before they become critical. Simplified explanation: imagine you're using a flashlight to find something in a dark room. A regular flashlight gives you a basic view, but a quantum-enhanced flashlight would shine far brighter and reveal even the smallest details, allowing you to spot objects in the room with incredible precision. In medical imaging, quantum-enhanced tools could detect even the faintest changes in the body. Quantum sensors could make medical imaging more sensitive and accurate, enabling doctors to detect problems at earlier stages when treatment is more effective. For example, quantum imaging could help in detecting early-stage cancer, monitoring brain activity, or tracking the effectiveness of treatments for chronic conditions like Alzheimer's disease. One promising development is the use of quantum magnetometry, which can measure magnetic fields with extreme precision. This could help detect the subtle changes in the brain's magnetic field that may indicate neurological disorders or even predict seizures in epileptic patients. Questions to ponder. How could quantum-enhanced medical tools change the way doctors diagnose and treat diseases? What impact could early detection of conditions like cancer have on survival rates? Quantum energy solutions, harnessing the power of the quantum world. Quantum mechanics could play a key role in solving one of the world's most pressing issues: energy. By exploiting quantum effects, scientists aim to create quantum batteries and improve solar energy systems, making them vastly more efficient than current technologies. Imagine a super-efficient battery that can store more energy, last longer, and charge faster than anything we have today. Quantum mechanics might unlock the secrets to building such batteries, revolutionizing energy storage and making renewable energy sources, like solar and wind, more reliable and accessible. Quantum-based energy systems could lead to advances in energy storage, energy generation, and transmission, addressing the challenges posed by renewable energy and the increasing demand for power in a growing world population. Quantum technologies could enable smarter energy grids that optimize the distribution of power, potentially solving some of the biggest energy problems. Researchers are working on quantum dot solar cells, tiny particles that can absorb light more efficiently than traditional solar panels. Quantum dots could allow solar panels to capture more light, turning more of it into usable energy, which would make solar power far more efficient and cost-effective. Questions to ponder. Could quantum energy breakthroughs make renewable energy more reliable and sustainable? How soon could quantum energy solutions be available to the general public, and what would their impact be on the global energy landscape? Quantum navigation, beyond GPS and the digital revolution. Quantum mechanics is also revolutionizing how we navigate the world. Quantum sensors are already being used to create GPS-independent navigation systems. These quantum sensors can detect incredibly subtle changes in gravitational and magnetic fields, enabling highly precise positioning without relying on satellite signals. Traditional GPS relies on satellites orbiting the Earth to pinpoint your location. But quantum navigation systems could use ultra-sensitive quantum sensors to detect the Earth's natural magnetic fields and gravitational pull, allowing you to navigate with pinpoint accuracy whether you're in a dense forest, a submarine, or on another planet. Quantum-based navigation systems could eliminate the need for GPS satellites, which are vulnerable to interference and hacking. They could also enable high-precision navigation in places where GPS signals are weak or unavailable, like deep underground, underwater, or in space. Quantum gyroscopes, which use quantum entanglement and superposition to detect the rotation of objects, could be used to create extremely accurate navigation systems. These gyroscopes are already being tested in aerospace and defense applications, but their potential for everyday use, like in autonomous vehicles or deep-sea exploration, is enormous. Quantum computing in cryptography, the dawn of unbreakable security. Quantum computing is poised to revolutionize cryptography by providing the means to create encryption systems that are theoretically unbreakable. Traditional encryption methods could become obsolete as quantum computers gain the ability to break them, but quantum cryptography offers a solution by using the principles of quantum mechanics to secure data in ways that classical systems can't match. Current encryption relies on complex mathematical problems that are difficult for classical computers to solve. But quantum computers can solve these problems much faster. On the other hand, quantum cryptography ensures that any attempt to intercept or tamper with encrypted messages would be immediately detectable, making hacking virtually impossible. As cyber attacks become more sophisticated, quantum cryptography could offer a future-proof solution. It promises to secure everything from personal communications to banking transactions to national defense secrets without the risk of being hacked by even the most powerful computers. Example: in 2020, China's MISIS satellite successfully transmitted quantum encrypted data across thousands of miles, demonstrating the potential for secure global communication using quantum technologies. Questions to ponder. What impact will quantum cryptography have on online privacy and security? Could quantum encryption help protect sensitive data from cyber attacks in the digital age? As we've seen, the real-world applications of quantum mechanics are not confined to theoretical physics. Labs, they are already shaping industries, technologies, and even our daily lives. From revolutionary medical imaging and energy solutions to quantum navigation and unbreakable cryptography, quantum mechanics is poised to transform every aspect of society. The future is quantum, and as we continue to unlock the mysteries of the quantum world, the possibilities are endless. Whether in health, energy, security, or computing, quantum mechanics promises a future where science fiction becomes science fact. As we continue to explore and harness these extraordinary technologies, we may be on the brink of a new era of innovation that will change the world forever. The quantum journey ahead. Quantum mechanics has taken us on a journey through the very fabric of reality itself, a realm where the familiar laws of physics are challenged and the impossible becomes possible. From the mind-bending properties of wave-particle duality to the profound questions it raises about time, consciousness, and our understanding of existence, quantum science pushes the boundaries of human knowledge and invites us to think in ways we never have before. We've explored how quantum mechanics is reshaping not only physics but philosophy, asking whether reality exists only when observed, and whether every possible choice creates a new universe. We've delved into the potential connections between quantum processes and consciousness, raising the possibility that the universe itself could possess a form of awareness. We've seen that quantum mechanics isn't just abstract theory, it's already changing the world in concrete ways. Quantum computing promises to revolutionize industries by solving problems that are currently beyond our reach. Quantum cryptography is set to make communication more secure than ever before. Quantum sensors and energy solutions could transform healthcare, navigation, and our global energy systems. The future of quantum science is a thrilling one. While there is still much to learn, the breakthroughs we've discussed could reshape entire industries, solve some of the world's most pressing problems, and open up new frontiers in technology and human potential. As quantum technologies continue to evolve, we are standing on the brink of a new era, an era where the strange, wonderful, and mysterious world of quantum mechanics becomes an integral part of our everyday lives. But perhaps the most important takeaway is this: quantum mechanics teaches us that the universe is far more interconnected, unpredictable, and beautiful than we ever imagined. Whether we're trying to unlock the secrets of consciousness or exploring new technologies, quantum science reminds us that there is still so much more to discover. We are only beginning to scratch the surface, and the future holds infinite possibilities. What if we could trace the origins of life itself? Why does the cosmos seem so perfectly tuned? Is the universe hiding its creator? Could the universe be alive? Is life a cosmic accident or a destined event? Are we truly alone in the universe? What if we could trace the origins of life itself? Is life on Earth a fleeting accident in an otherwise indifferent cosmos? Or is it a necessity written into the very fabric of the universe? Perhaps, even more astonishingly, could it be the deliberate creation of a higher intelligence? These questions have fascinated thinkers, scientists, and philosophers for centuries, pushing the boundaries of human imagination. The mystery of how life began is one of the deepest questions humanity has ever pondered. Despite centuries of progress in science and technology, the origins of life remain shrouded in uncertainty, leaving us to speculate at the intersection of science, philosophy, and even metaphysics. From the chaotic dance of atoms billions of years ago to the emergence of complex, sentient beings, the journey of life has ignited debates across disciplines. Is our existence the result of sheer chance, inevitable under universal laws, or the product of a higher, intentional design? Each perspective offers a unique lens, but none can yet claim to hold the definitive answer. This exploration will journey through three primary perspectives: the hypothesis that life arose by coincidence, the argument that life was an inevitable outcome of nature's laws, and the possibility that a higher consciousness designed the conditions for life to emerge. Through these lenses, we'll uncover the profound implications of each theory, examining evidence, raising questions, and contemplating what it all means for our understanding of existence. Coincidence, the role of randomness in life's origins. Life, in this view, is nothing more than a fortunate accident, a consequence of countless random interactions occurring under the right conditions. Imagine a chaotic primordial Earth, its surface bombarded by meteors, its atmosphere thick with gases, and its oceans bubbling with chemicals. Amid this seemingly anarchic environment, molecules collided, bonded, and eventually formed the building blocks of life. This hypothesis suggests that life is not guaranteed, but rather the result of an almost miraculous convergence of circumstances. It argues that, given the vastness of time and space, such a cosmic accident was bound to occur somewhere. Earth just happened to be the lucky winner in the lottery of existence. Abiogenesis, the scientific explanation for life's origins, posits that life arose naturally from non-living chemical compounds. This theory gained traction with the famous Miller-Urey experiment in 1953. In a controlled laboratory setup simulating early Earth's conditions, researchers exposed a mixture of water, methane, ammonia, and hydrogen to electric sparks, mimicking lightning. Remarkably, the experiment produced amino acids, organic compounds essential for life. The results were groundbreaking, proving that complex molecules could form spontaneously under the right conditions. Subsequent research has expanded on these findings, identifying potential pathways through which simple molecules could organize into self-replicating systems, the precursors to life. However, abiogenesis faces significant challenges. Critics point out that forming life's essential components, like proteins or RNA, is far more complex than creating amino acids. Even under ideal conditions, the probability of assembling functional proteins by chance is astronomically low, leading skeptics to question whether randomness alone could account for the emergence of life. Let's consider the staggering odds involved in life's emergence. The chance of a single functional protein forming spontaneously has been compared to a monkey typing out Shakespeare's Hamlet by randomly hitting keys on a keyboard. Now multiply that improbability by the complexity of an entire living cell. Scientists estimate that Earth existed for approximately 1 billion years before life emerged. While this time frame provides countless opportunities for chemical interactions, it also underscores how rare and extraordinary the conditions must have been for life to begin. The coincidence hypothesis raises a critical question. If life is a rare accident, why does the universe appear so finely tuned to allow it? For instance, the Earth orbits in the Goldilocks zone, where temperatures are just right for liquid water, a key ingredient for life. Some argue that this perfect alignment is too precise to be purely coincidental. Others counter that the universe's vastness ensures some planets would inevitably meet these conditions. To grasp this perspective, think of the universe as a vast casino, and Earth's origins as a game of roulette. The odds of life forming may have been infinitesimally small, but the wheel spun countless times across the cosmos. Earth, it seems, was the one lucky spin where the ball landed perfectly. The hypothesis that life arose by coincidence paints a picture of a fragile, improbable event in the grand chaos of the universe. Yet, this perspective also leaves us with a profound sense of uncertainty. If life truly is a cosmic accident, what does that say about its meaning or lack thereof? Necessity. Life is an inevitable outcome. Unlike the randomness of the coincidence perspective, the necessity hypothesis suggests that life was bound to happen. It argues that the physical and chemical laws governing the universe naturally lead to the emergence of life when conditions align. In this view, life is not a miraculous anomaly, but an inherent outcome of the universe's design, a natural expression of its potential. Imagine the universe as a carefully arranged orchestra. Every instrument, from gravity to electromagnetism, plays its role, creating conditions that make life not only possible but unavoidable. Life's building blocks rely on universal principles that drive molecules to organize into more complex forms. Consider the following: the Goldilocks zone. Earth orbits the Sun at just the right distance, allowing liquid water to exist, a critical factor for life. Many other planets in the universe may share similar conditions, suggesting that life could arise wherever these just right circumstances occur. Self-organization in chemistry. Certain molecules have an innate tendency to self-organize. For example, phospholipids spontaneously form membranes in water, mimicking the cell walls of living organisms. This self-assembly hints that life's essential structures could arise naturally under the right conditions. This perspective gains further support from extremophile organisms that thrive in extreme environments. From hydrothermal vents deep in the ocean to boiling acid springs, life has demonstrated its remarkable ability to emerge and survive in diverse conditions, reinforcing the idea that it may naturally arise wherever it can. The idea that specific chemical reactions, under specific conditions, inevitably lead to life. For instance, amino acids tend to link together when exposed to certain environmental pressures, potentially forming proteins over time. The role of water and carbon. Water's unique properties, like its ability to dissolve a wide range of substances, make it a crucial solvent for biochemical reactions. Similarly, carbon's versatility allows it to form complex molecules, such as DNA and proteins, making it the backbone of all known life. Astrobiological discoveries. Recent discoveries of organic compounds on comets and meteorites suggest that the building blocks of life are not unique to Earth. These findings bolster the argument that life's raw materials are widespread in the universe, increasing the likelihood of its emergence. Extremophiles challenge the notion that life requires Earth-like conditions. Organisms like the tardigrade can survive in the vacuum of space, extreme radiation, and intense heat. These resilient creatures suggest that life might emerge in environments we once deemed uninhabitable. Moreover, the search for exoplanets has revealed thousands of potentially habitable worlds. Some of these planets orbit stars similar to our Sun within their own Goldilocks zones. Could these planets host life? If so, it would support the idea that life is a universal phenomenon, not a unique accident. Yet, if life is inevitable, why have we not found definitive evidence of it beyond Earth? This paradox, known as the Fermi paradox, challenges the necessity hypothesis. Are we simply not looking in the right places, or is life's emergence rarer than we assume? The silence of the cosmos raises as many questions as it answers. Think of life as a seed planted in fertile soil. The conditions, sunlight, water, nutrients, make growth inevitable. Similarly, when the universe provides the right soil and climate, life, like a seed, is destined to flourish. The necessity hypothesis paints life as an intrinsic part of the universe, woven into its very fabric. This perspective shifts the narrative from randomness to inevitability, suggesting that wherever the universe creates the right conditions, life will arise. Design, a higher consciousness behind life. What if the emergence of life was not a product of random chance or inevitable natural laws, but a deliberate act of creation? The design hypothesis proposes that life's complexity and the universe's apparent fine-tuning point to the influence of a higher intelligence, a consciousness that set the stage for life to arise. Imagine a watch found on a beach. Its intricate gears and precision are unlikely to have formed by accident. Similarly, proponents of this view argue that life's complexity, from DNA's coded instructions to the universe's finely tuned physical constants, suggests a purposeful design rather than coincidence or inevitability. The idea of a higher consciousness shaping life is deeply rooted in philosophical and spiritual traditions. Religious perspectives, creation stories from various cultures such as Genesis in the Bible, Brahma's creation in Hinduism, or the Dreamtime of Aboriginal Australians, often portray life as the intentional work of a divine being or higher force. Philosophical inquiry. Ancient philosophers, including Plato and Aristotle, posited the existence of a prime mover or intelligent designer who set the cosmos into motion. These narratives resonate with the design hypothesis, reflecting humanity's long-standing intuition that life and the universe may hold deeper meaning and purpose. The fine-tuning of the universe. Certain physical constants, such as the strength of gravity, the charge of the electron, or the cosmological constant, are finely balanced. Even the slightest deviation in these values would render life impossible. For example, if the strength of gravity were slightly weaker or stronger, stars could not form or sustain nuclear fusion, eliminating the possibility of planets and life. The fine-tuning argument suggests that these precise values are unlikely to have arisen by chance, pointing instead to intentional calibration. The DNA code as evidence of design. DNA, often referred to as the blueprint of life, is a molecular code that governs the development and functioning of all living organisms. Its complexity and specificity have led some scientists and philosophers to liken it to a computer program. Could such intricate programming have arisen without an intelligent programmer? Irreducible complexity. Some biological systems, such as the bacterial flagellum or the human eye, are so complex that they seem irreducible, incapable of functioning if any single part were removed. Proponents argue that such systems challenge the gradualist explanations of evolution, suggesting a designer's hand. While compelling, the design hypothesis has faced significant criticism. Anthropocentrism. Critics argue that intelligent design is anthropocentric, projecting human notions of purpose and complexity onto the universe. Lack of empirical evidence. Unlike scientific theories that can be tested and falsified, intelligent design often relies on inference, which some dismiss as unscientific. Alternative explanations. Mechanisms like evolution and natural selection offer robust explanations for life's complexity, reducing the need for invoking a designer. In recent years, some scientists have explored ways to reconcile the idea of design with empirical evidence. Simulation theory. The hypothesis that our universe is a simulation designed by an advanced intelligence. Proponents like physicist Nick Bostrom argue that if future civilizations develop the technology to simulate universes, it's statistically likely that we are living in one. Panpsychism, a philosophical view suggesting that consciousness is a fundamental property of the universe, embedded in all matter. In this framework, the universe's design could emerge from a collective consciousness rather than an external creator. To understand the design hypothesis, think of life as a symphony. The universe is the orchestra, and its laws are the instruments. A symphony requires a conductor to arrange the notes into harmony, just as life's emergence might require a designer to orchestrate the right conditions. Comparative analysis overlapping themes and conflicts. Despite their differences, the three perspectives, coincidence, necessity, and design, share common ground in addressing the profound mystery of life's origins, the uniqueness of life. All three views recognize that life is extraordinary, whether it emerged by accident, inevitability, or design. Each perspective underscores the rare and complex nature of living systems in a vast, seemingly indifferent universe. Interplay between chaos and order. The coincidence hypothesis highlights the chaotic randomness of molecular interactions. The necessity hypothesis demonstrates how order emerges naturally from the laws of physics and chemistry. The design hypothesis emphasizes intentional order, suggesting chaos is merely the backdrop for a purposeful plan. The role of universal laws. All three approaches acknowledge the importance of the universe's physical and chemical laws. Whether these laws create life by chance, inevitability, or design, they are fundamental to the discussion. While the shared themes bring the perspectives together, their underlying assumptions often lead to sharp contrasts. Chance versus determinism. Coincidence relies on randomness, viewing life as the result of improbable events. Necessity emphasizes determinism, positing that life is a predictable outcome of universal principles. Design versus naturalism. The design hypothesis introduces the idea of a higher intelligence or purpose, while coincidence and necessity remain rooted in natural processes, rejecting the need for external intervention. Philosophical implications. Coincidence suggests life has no intrinsic meaning, as it is a random occurrence. Necessity offers a middle ground, implying that life has significance as a natural product of the universe. Design infuses life with purpose, proposing that it is part of a deliberate cosmic plan. Some thinkers argue that these perspectives are not mutually exclusive but could instead represent different layers of the same reality. The coexistence of chance and necessity. Life's origins could involve a combination of random events and deterministic laws. The formation of essential molecules might be random, but their assembly into complex systems could follow inevitable patterns. Design through natural processes. The design hypothesis doesn't necessarily conflict with science. A higher intelligence might have created the universe's laws in such a way that life emerges naturally, with occasional elements of randomness shaping its path. To visualize these perspectives together, imagine a painter creating a masterpiece. Coincidence. The paint splatters randomly on the canvas, forming an unplanned image. Necessity. The painter uses precise strokes guided by the properties of the brush and paint, ensuring the painting emerges logically from the tools. Design. The painter has a vision from the start, intentionally guiding every element of the painting toward a final purpose. Perhaps life's origins resemble a collaboration between these approaches, an interplay of chaos, inevitability, and vision. The origins of life remain one of humanity's greatest mysteries, inspiring theories that range from randomness to inevitability to intentional design. Coincidence reminds us of life's fragility, portraying it as a miraculous anomaly in a chaotic universe. Necessity elevates life to a fundamental feature of the cosmos, a product of its inherent laws and principles. Design introduces purpose, suggesting that life may be the deliberate creation of a higher intelligence. Each perspective provides a compelling lens, yet none alone can fully explain the profound complexity and meaning of life's emergence. As we journey through these ideas, one question emerges: must we choose just one? Perhaps life's origins encompass all three perspectives in a complex interplay. Coincidence could describe the unpredictable initial conditions that led to life. Necessity could explain the universal laws that guided its development. Design might reflect an underlying purpose woven into the fabric of the cosmos. Much like a mosaic, the full picture of life's origins might only emerge when we consider these perspectives together, embracing their unique insights and shared mysteries. The exploration of life's origins ultimately leaves us with more questions than answers. If life is a cosmic accident, How do we make sense of its meaning, or lack thereof? If life is inevitable, what responsibilities do we have as part of the universe's natural progression? If life is designed, what role might humanity play in a grander plan? As we contemplate these questions, we are reminded that the journey to understand life's origins is as important as the answers themselves. As we gaze into the night sky, marveling at its vastness and mystery, one truth becomes clear. Our existence is an extraordinary phenomenon, whether born of chance, necessity, or design. It is up to us to make meaning from this knowledge, to explore with curiosity, and to live with purpose. For in the grand tapestry of the universe, we are both its observers and participants, a fleeting but vital spark in the eternal story of existence.